thanks for your introduction, Mr. Bettini. Right?
Fine.
Okay. If we think of beam welded, beam welds and structural steels, we usually have think of relatively high weld toughness compared with monolithic structure, and thus low toughness in the weld seam. If we use those welds in low ambient temperatures and we have crack-like defects due to the production process, the welding itself, cyclic crack growth can occur due to cyclic loading. I'm sure that this is fine. Due to cyclic loading during operation until it reaches a critical crack size, and there is a risk of brittle failure for these components. We are the first one to think of this scenario, but it has been used as a scenario for standards, especially in the Eurocode 3, the part 110, which is a guidance for the selection of steels taking into account fracture toughness. It has been verified for base metals and arc-welded components. And one central element that they use is a correlation between the fracture toughness taken from Charpy energy values and the T0 temperature from the fracture toughness master curve, known as the fracture toughness reference temperature. So the Sanz correlation reads as T0 is T27 Joule minus 18 degrees, and depending on the literature you use, you find either 1 sigma or 2 sigma deviation, with sigma being roughly about 13 degrees. And we asked ourselves, can the Sanz correlation be used for electron beam welded joints as well? For our research, we used 3 different steel grades. The lowest yield strength was around 355 megapascal, going up to 960 megapascal. They were electron beam welded with a voltage of 120 kilovolts, a beam current of 35 milliampere, a welding speed of 10 millimeters per second, which is rather fast if you compare it, for example, to arc-welded specimen. The sheet thickness was chosen to be 10 millimeters, and we recorded temperatures during welding, and the T85 temperatures, the cooling times from 800 degrees to 500 degrees could be determined to be 1.6 seconds. After welding, we took cross sections perpendicular to the welds, and we made a hardness measurement on the surface of these cross sections. And you can see the results in this figure, and it could be shown that the hardness within the weld seam exceeded 400 vicas, and in the base material it was dependent on the base material, of course, and we have a relatively high mismatch ratio between the hardness in the S355 specimen between the hardness in the weld seam and the hardness in the base metal. For our tests, we took the specimen transfers to the weld seam. They were all notched in the middle of the weld seam, and the fracture toughness testing was done to create a fracture toughness master curve according to the American standard E1921, which needs at least 6 valid specimens. We chose a ratio of the initial pre-crack compared to the specimen height of roughly 0.5. The specimen were side grooved after pre-cracking, and the J integral was determined and transformed into the plastic stress intensity factor KJC. If we think of Charpy toughness testing of beam welded steels, we shortly have to discuss that they behave differently compared to arc welded specimen or base metals. We have basically 3 failure patterns that usually occur. The one failure pattern which gives us information about the weld seam itself is a brittle fracture within the weld seam. And with rising temperatures, we usually can determine crack path deviation either into the fusion zone or into the base metal. The reason for this behavior is basically the relatively narrow weld geometry and the high mismatch ratio of the hardness between the weld seam and the base material. As we want to connect the behavior of our beam welds, we chose only the specimen that failed with the first failure pattern, because that are the only ones who give us information about the beam, about the weld itself. And as the failure behavior changes, it is difficult to use the normal compensation curves which have a sigmoidal slope. So we use compensation curves for the specimen we chose for our correlation. If we have a look at the experimental results for the Charpy toughness transition curves, it occurred that we weren't able to detect the brittle fracture within the weld seam for the S355 welds. We saw crack path deviation into the fusion zone even at relatively low temperatures. In case of the S690 and S960 metals, we were able to determine failure in the weld seam itself. So we can speak of an intrinsic T27 value that could be determined. This table summarizes the values we found. So for the S355 specimen, we had crack path deviation even at relatively low temperatures. So the T27 temperature isn't valid for our correlation. The temperature that was estimated for the S690 was minus 38 degrees, and for the S960 it was minus 10 degrees Celsius. The fracture mechanic test showed that all the specimen failed within the weld seam, so we didn't see any crack path deviation. We could ascertain the reference temperature T0 for all the 3 data sets. And if you compare this reference temperature with arc welded steels or base materials, they are relatively high. First conclusion can be drawn that the failure behavior during the Charpy toughness tests is different than the failure behavior during the fracture mechanic tests. So we cannot conclude one macroscopic failure pattern which occurs in the Charpy toughness tests and predict the macroscopic failure behavior for our fracture toughness tests or for welded components. If we look at our results in terms of the Sanz correlation, we have here the T27 joule temperature and the T100 temperature in our diagram. This dark gray line shows the Sanz correlation, and that should be the line where we would expect our results to be if the Sanz correlation could be used for this kind of steels. We could use the data points for the S690 and S960 to use it in this kind of correlation, and we can see that the determined T0 temperature is much higher than the expected value. We have values between the 1 sigma and 2 sigma deviation line. That shows that the Sanz correlation does not lead to conservative results in our case, and another correlation has to be found. As we don't have that much points, we weren't able to find a correlation yet, but that is part of the research that is going on right now. To sum it up, we can say for the Charpy toughness test, that the sigmoidal compensation curves, which are usually used, aren't suitable due to the change in fracture behavior, and that the high mismatch ratio of the S355 welds led to crack path deviation even at relatively low temperatures, which means we couldn't find an intrinsic toughness value with the help of the Charpy toughness tests, and we couldn't use it in the Sanz correlation. The fracture behavior showed us that the macroscopic fracture pattern, if we speak about crack path deviation, cannot be transferred from the Charpy V0 specimen to fracture mechanics specimen. And if we regard the question whether the Sanz correlation is suitable for the beam welded steels, we can say it could be applied to the investigated S690 and S960 welds. It surely isn't applicable for welds with high mismatch ratios, and as it doesn't show conservative results, another correlation has to be found. So thank you for your attention.